Good evening, all of you. I am Pia Needu, Research Scholar, PG and Research Department of Mathematics, Maharajas College, Ernakulam. I am doing PhD under the guidance of Dr. Bloomy Joseph, Head of the Department of Mathematics, Maharajas College, Ernakulam. As a part of Research Scholar webinar series, organized by the Research Committee and IQAC of Maharajas College, Ernakulam, I wish to give a talk on topology, a geometrical view. Is the screen clear?
Yes, visible.
Is it okay now?
Yes.
So, it is easy to understand the concepts if we can view it geometrically. So, we can start with first, what is a topology? The word topology is derived from two Greek words, topos and logos. Topos meaning surfaces and logos meaning study. Topology thus literally means the study of surfaces. From this, we can understand that topology is a sort of geometry. In geometry, we deal with concepts like the area, volume, and curvature, etc. But we are not studying about color, smell, taste, etc. Why it is so? In geometry, we study about geometrical properties only. So, what are these geometrical properties? If a property of an object is given in a space, how do we know that it is a geometrical property or not? So let us consider an example first. Consider two triangles ABC and triangle EFG and assume that its sides are equal, that AC is equal to EG, AB is equal to EF, and BC is equal to FG. That means they are congruent to each other. Also, we can say that the perimeter of triangle ABC is equal to the perimeter of triangle EFG, and area of triangle ABC is equal to area of triangle EFG. So from this, we get that perimeter and the area of the triangles are equal as they are congruent to each other. Suppose if I am coloring the triangle ABC with red, and EFG can take any color, need not be red color. That means color is not preserved under congruence. That is why it is not a geometrical property. So geometrical properties are properties which are invariant under congruence. So my next question is, what is congruence? How we can say two objects are congruent? Let us consider this example. By seeing this figure, how can we get the triangle EFG from triangle ABC? Looking at the figure, we can see that if we shift the triangle ABC to the right side, we can get triangle EFG. So my question is, can we find a transformation f from R2 to R2 such that f of triangle ABC is equal to triangle EFG? Yes, we can. That transformation is called translation. So if O1 and O2 belongs to R2, if there exists a translation from R2 to R2 such that f of O1 is equal to O2, then O1 and O2 are congruent. So we can say two objects A and B are congruent to each other if there exists a bijection f from A to B such that d of xy is equal to d of f of x, f of y. That is, the distance between two objects, distance between the 2 points of the first object should be equal to the distance between the corresponding point of the image object. Other than translation, we can have different transformations, different types of transformation, such as rotation, reflection, and its combination, etc. First, we can look at what is a rotation. If I am considering two triangles ABC and EFG, the triangle EFG, by looking at the figure, we can say that the triangle EFG is obtained by just rotating the triangle ABC. And this we can see that the case of reflection, the rectangle PQRS is just the reflection of the rectangle ABCD. In addition to this, any combination of these is also a transformation. That is, rotation reflection is a combination, translation rotation is a combination, translation reflection is a combination. So these are all transformations. So in all these, we can say that the distance between 2 points of the first object is the same as the distance between the corresponding of the second object. Thus, we can say geometry is the study of those properties which are invariant under congruence. And to this group of transformations, if we are going to include stretching, blowing, shrinking, bending, all type of such transformations, we get it by continuous transformations. That is, suppose that if we are taking a rubber band, we are stretching it, and if we release it, it comes to its original position. That is, there is a continuity. If we can do one way continuously, we can do it other way also continuous. If we are blowing a balloon, after blowing it, it makes a other shape. If we are releasing the air, it comes to the original shape. There is also a continuity. The thing should be remembered is that they shouldn't break. That is, if we are stretching a rubber band, it comes to the original position unless it breaks. If it is breaking, it is not possible. So we are getting a group of bicontinuous transformation. That is a group of homeomorphism. This geometry is called topology. That is, topology is the study of topological properties, and topological properties are properties which are invariant under homeomorphism. So what is a homeomorphism? Homeomorphism is a bijective function where f and its inverse are continuous. So look at these examples. These are topologically equivalent, but they are not geometrically equivalent. The first one, if you are taking a rectangle, we can deform it into a circle. They are topologically equivalent. The second one also, the circle can be made into a somewhat rectangle shape where the sides are smoothened, and it can be made into correct rectangle form. So here all they are deformed without breaking. So they are deformed and they are equivalent. They are topologically equivalent, but they are not geometrically equivalent. And in this one, the mug is made into a form of a torus. By pressing and deforming the mug without breaking it, it can be made into a shape of a torus. These are some examples for homeomorphic objects. Here, the this line can be stretched and it can be bended in some other form. Similarly, the circle can be made into a rectangle and it can be made into some other form without breaking. But in the case of here non-homeomorphic object, the first one, this is breaked into two. So a continuity is gone. That is, the connectivity is gone here. So we can't say that these are homeomorphic objects. These are non-homeomorphic objects and these are homeomorphic objects. In homeomorphic objects, no breaking must be happened. That is, connectivity should never go. From all these, we can say that topology is a sort of geometry which is a geometry of connectivity also. So topology is a geometry of connectivity. So to make it more clear, I will give you an example. Take a balloon and put a point on the balloon and draw a circle around the point, such as the point lies inside the circle. Now blow the balloon. Even though after blowing the point will lie inside the circle, the point will not go unless it breaks. That is, the interior and exterior will not change unless it breaks. While breaking, the property will lose. That is, so by breaking, what we lose is its connectivity. So connectivity shouldn't go. So topology is considered as the geometry of connectivity. So sometimes also say that topology is a rubber sheet geometry. That is, all stretching, bending, etc. is possible here. As stretching bending all is possible here, we can say topology is also a rubber sheet geometry. So the sum and substance of this session is that geometry is the study of geometrical properties, and geometrical properties are properties which are invariant under congruence. And topology is the study of topological properties, and topological properties are properties which are invariant under homeomorphism. Also, topology is a geometry of connectivity, and topology is also known as a rubber sheet geometry. With this, I conclude my section. Thank you.